We begin far above the noise of daily life. Out here, Earth doesn't look like a complicated place. It looks simple. A quiet sphere turning in sunlight, a soft blue curve, white weather drifting like slow breath. From this distance, it's easy to imagine the planet as solid and straightforward, like a smooth stone you could hold in your hand. But Earth is not a stone. It's layered, it's active, it's warm inside, and most of what makes it Earth is hidden beneath the surface you live on. If you remember the classic textbook picture, Earth sliced open like a diagram, you've seen the labels: a thin crust, a thick mantle, and a core, divided again into an outer liquid layer and an inner solid one. The oceanic crust is often described as only about 5 to 10 kilometers thick. The continental crust is thicker, often tens of kilometers, sometimes 30 to 50 or more, depending on where you are. And then the mantle, mostly silicate rock, continues downward for nearly 3,000 kilometers. Below that, the core, largely iron and nickel. An outer core that behaves like a liquid, roughly a couple thousand kilometers thick, and an inner core, solid under immense pressure, roughly 1,000 kilometers across in thickness. It's a clean picture, a tidy story, and tonight's calm question is simply, how do we know any of that when we can't actually go there? Because if you think about it, it's strange. Humanity has sent spacecraft across billions of miles. We've landed robots on Mars. We've flown past Saturn, past Neptune. 2 Voyager probes have crossed the edge of the Sun's influence into interstellar space. And yet, when we try to go downward into our own world, we barely scratch the skin. Even from orbit, you can sense the thinness of that skin. The continents and ocean basins, the entire familiar surface, are like a film on top of a much larger body. If Earth were scaled down to the size of a standard classroom globe, the crust would be thinner than a coat of paint. The deepest mines are only a few miles down. In South Africa, the Tautona gold mine reached close to 4 kilometers below the surface, about 2.5 miles. For the people who worked there, the rock above their heads was not an idea. It was a real weight. Heat rose from below. Air had to be moved and cooled. The planet reminded you, physically, that down is different from up. In the United States, the Bingham Canyon mine in Utah, one of the largest open-pit mines on Earth, drops more than a kilometer deep. From above, it looks like a giant spiral carved into the land, like a slow-motion canyon made by machines. But none of that comes close to the depths we're talking about tonight. The boundary between Earth's crust and mantle can be tens of kilometers down. The mantle itself stretches for thousands of kilometers, and the center of Earth, the core, rests more than 6,300 kilometers beneath your feet. That's nearly 4,000 miles. So the obvious question follows naturally. If the deepest human-made hole is only about 12 kilometers, about 7.6 miles, how can we confidently talk about things that are hundreds or thousands of miles down? That famous record belongs to the Kola super-deep borehole, drilled during the Soviet era on the Kola Peninsula. It reached about 12,262 meters, so precise a number because science loves precision. The drill went down for years, and even then, it didn't come close to the mantle. And there's a reason it's hard to go deeper. It isn't just the distance, it's the environment. As you drill down, temperature rises, pressure rises. Rock that seems rigid at the surface begins to behave differently. Over long time scales, deep hot rock can flow, slowly, like something between solid and liquid plastic, stubborn, heavy. Drill bits wear, holes deform. The earth resists being entered. So if we can't reach the mantle, and we can't touch the core, how do we know the core exists at all? The answer is one of the most comforting ideas in science. You don't always need to see something directly to understand it. Sometimes you can learn by listening. Sometimes you can learn by watching how a world responds when it's disturbed. And Earth is disturbed, gently and not so gently, all the time. The surface you live on isn't one unbroken shell. It's broken into large plates, rafts of lithosphere drifting slowly across the planet. From space you can't watch them move in real time. The motion is too slow for a human eye. But over years and decades and millions of years, the movement is undeniable. Along the edges of these plates, the planet creaks. In places like California's fault systems, the Aleutian Arc of Alaska, and the long curve of the Pacific Ring of Fire, plates meet, press, slide, and sometimes lock together, storing energy like a bent spring. When the lock releases, the stored energy becomes motion, and motion becomes waves. Tonight, from this calm orbit above the clouds, we're going to do something simple. We're going to listen to Earth, not with ears because the vacuum of space is silent, but with instruments that can sense motion smaller than a heartbeat. In hospitals, doctors use ultrasound to see inside the body. They send sound waves in and they read the echoes. They don't open you up to look at your organs. They measure how waves move through different tissues. Earth science uses a similar logic on a planetary scale. Instead of ultrasound, we use seismic waves. Instead of a handheld probe, we use a global network of sensitive instruments called seismometers, quiet boxes that turn tiny ground motions into data. And instead of one patient lying still, our patient is a planet that occasionally shudders, releasing waves that race through rock, metal, and molten layers, carrying information like a message in motion. Around the world, these instruments work together like a quiet choir. A large earthquake in the Pacific can be recorded in the Midwest. A deep quake beneath Japan can be traced by sensors in Alaska, in California, in New England, because the whole planet conducts the vibration. When you collect recordings from many directions, you can begin to treat Earth like a transparent sphere, not to light, but to motion. Across the United States, agencies like the USGS help monitor earthquakes, and research networks, many supported by universities and the National Science Foundation, collect continuous seismic records. Large projects such as EarthScope helped deploy thousands of sensors across North America, building a map of deep structure the way a doctor builds an image from many slices. And earthquakes aren't the only signal. For shallow imaging, scientists sometimes use controlled sources, vibration trucks, air guns offshore, and other carefully designed methods to send known pulses into the ground and read their returns. Historically, Even large explosions have left clear seismic fingerprints, simply because the start time and location are known precisely. Those signals helped refine measurements the same way a calibration tone helps tune an instrument. But for probing the deep interior, the mantle, the core, nature provides the strongest source on a regular basis. Earthquakes. All of it begins with the same simple event: a sudden slip along a fault and a pulse of energy spreading outward. An earthquake is not one wave. It is a whole family of waves, each with its own behavior. Some ripple along the surface, shaking cities and coastlines. But the most useful waves for exploring Earth's interior are the ones that dive into the planet and cross it, tracing long, curved paths through a globe. They are called body waves, and there are two main kinds. The first are P waves, short for primary waves, because they arrive first. P waves are compressional waves. They squeeze and release the material they travel through, like a slow pulse moving down a spring. The second are S waves, secondary waves, because they arrive later. S waves are shear waves. They move material side to side, like a rope being flicked. This difference sounds small, almost poetic: compression and shear. But it contains the key to the deepest secret beneath the crust, because P waves can travel through solids and liquids. S waves can travel through solids, but they cannot travel through liquids. Not because science is being picky, because liquids don't support shear in the same way solids do. A liquid can be squeezed, it can be compressed, but it can't hold a sideways pull long enough to pass it along as a wave. So if we send these two waves into Earth, and we see P waves arrive in places where S waves never do, we learn something quietly profound. Somewhere inside Earth, there must be a layer that behaves like a liquid. And from that calm, simple observation, the outline of the core begins to appear. In the next part, we'll watch how these waves curve, bend, reflect, and disappear into shadow zones on the far side of the planet's dark regions, on a seismic map that exists for the same reason an eclipse exists, because something inside Earth blocks the path. And when you find what blocks a wave, you begin to find what Earth is made of. For now, from this peaceful view above the atmosphere, let the questions settle like soft snowfall. Below us, the night side turns into view city lights, like scattered embers, coastlines faintly outlined, storms curling silently. And beneath all of it, far under the ocean and the continents, the same waves continue their long travel, bending through dense rock, passing through hidden layers, telling their story in timing and silence. We don't know Earth's interior by digging. We know it the way we know the inside of a bell, by listening to how it rings. From orbit, earthquakes are invisible. You don't see them the way you see storms. No spiral clouds, no lightning flicker, but the planet knows. When a fault slips, sometimes by only a few feet, the energy released doesn't stay local. It spreads outward through the globe, like ripples traveling through a bell after it's been struck. And if you have instruments scattered across the surface, quiet, patient sensors that never sleep, you can record those ripples as they arrive. In the United States, Networks coordinated through groups like IRIS and monitored alongside agencies like the USGS have helped build a long, continuous record of Earth's motion. Not just big quakes, but the constant background trembling of the planet, tiny vibrations from ocean waves, wind, even human activity. Because the truth is, Earth is almost never still. But when a strong earthquake happens, it produces a clean, powerful signal clear enough to read at great distances. And the way we read it is surprisingly gentle. We watch the timing. A seismometer doesn't show you a picture of the core. It gives you a trace, a seismogram where the ground motion rises and falls over time. On a single station's record, you can often pick out the first arrival, the P wave. Then, a little later, the S wave arrives. Then comes surface waves, slower, often larger, rolling around the planet's skin. But the real magic begins when you compare many stations at once. If you know where the earthquake happened, and you know where your stations are, you can measure how long the waves took to get there. And if you do that for enough earthquakes and enough stations, you start to build a map of the planet's interior, not by sight, but by travel time. It's like learning the shape of a dark room by listening to echoes, not by one echo, by thousands. Why the wave paths are curved. There's a quiet detail that matters here. If Earth were a perfectly uniform sphere, same material, same density everywhere, then seismic waves would travel in straight lines through it, and their speeds would be easy to predict. But Earth isn't uniform. Pressure increases with depth, and with pressure, density tends to rise. Even when the material stays rock, it becomes rock under different conditions, hotter, more compressed, more reluctant to deform. In general, seismic waves move faster through stiffer, denser material. So, as a wave dives deeper, it often enters regions where it can travel faster, and that causes refraction, the bending of its path. You've seen refraction in everyday life. A straw in a glass of water looks broken at the surface because light changes speed in water compared to air, and the path bends. Seismic waves do the same thing, except the water is deeper, denser earth. So instead of straight lines, the wave paths curve, arcing down into the planet and then back up. From space, if you could visualize them, Earth would look like it's filling with faint, translucent ribbons, millions of invisible arcs, all racing outward, all following the changing physics beneath the crust. The first great boundary, the moho. Early in the 20th century, scientists began noticing something odd in the timing. For a while, P waves would arrive at stations with a predictable delay. Farther stations recorded the waves later, closer stations earlier. That's expected. But beyond certain distances, some stations recorded P waves arriving sooner than they should have, like the waves had found a faster route. They had. In 1909, the Croatian seismologist Andrija Mohorovičić studied earthquake records and realized the most elegant explanation was a boundary inside Earth, a sudden change in material properties where waves speed up. That boundary is now called the Mohorovičić discontinuity, usually shortened to the MOHO. It marks the transition between the crust and the mantle. Think of it like this. Some seismic energy travels through the crust. Some dives deeper hits the faster mantle, and then returns to the surface. The deeper path can arrive first, not because it's shorter, but because it's faster for a large part of the journey. That single insight, based on timing, opened a door, because once you accept that there are boundaries inside Earth, you can begin to measure them. Over the decades, methods improved. The global network grew, and the MOHO stopped being a single depth and became what it truly is, a surface that varies around the world. Under the ocean, the crust is thinner, often just a few miles thick. Under continents, it thickens. Under major mountain ranges, it can become thicker still. In North America, for example, the crust beneath parts of the western mountain belts can be significantly thicker than beneath the central interior. The details are complex. Earth rarely draws clean lines, but the overall pattern holds. Ocean crust, thin. Continental crust, thicker. Some regions, thicker still, shaped by collisions, rifting, and deep history. From orbit, you can't see those thickness variations directly, but you can infer them by the way Earth carries waves. A planet with shadow zones. Now we move to a deeper, stranger discovery. When earthquakes happen, waves travel outward in all directions. That suggests that, with enough stations, you should be able to record them everywhere. But Earth surprised us. There are regions on the far side of an earthquake where certain waves don't arrive the way you'd expect. Places where the signal fades or disappears or arrives in a distorted, delayed form. Seismologists call these regions shadow zones. A shadow zone isn't a metaphor. It's a real pattern in the data. Areas where wave arrivals are missing or altered. And shadow zones are one of the clearest reasons we know Earth cannot be solid all the way through. Here's the calm logic. S-waves cannot travel through liquid. And yet, S-waves are recorded at many distances. And then, beyond a certain angular range around the planet, they vanish. They don't fade a little. They stop. That absence is information. It tells us that somewhere deep inside Earth, there must be a layer behaving like a liquid, large enough to block S-waves on paths that would otherwise reach distant stations. That layer is what we now call the outer core. P-waves behave differently. They can travel through liquid, but they slow down and refract strongly when they enter it. So P-waves also create a shadow zone different in shape, but just as meaningful. In other words, somewhere deep inside Earth, seismic rays encounter a boundary so dramatic that it bends their paths away from certain regions, leaving a gap like a quiet missing note in a song. And from that missing note, the outline of Earth's core emerges. In the next part, we'll move from this broad realization there must be a liquid core to the precise boundaries scientists measured. The depth where the mantle ends and the core begins. And then, even more surprisingly, the discovery that inside the liquid core there is another core, solid, dense, and hidden, revealed not by digging, but by faint reflected waves that arrive where they shouldn't. For now, just rest in the simplicity of the method. We don't need to touch the core to learn about it. We let the planet speak in vibrations, and we learn to hear the structure in the timing. Above the clouds, Earth rotates quietly. Below the crust, the mantle moves slowly, so slowly that it feels like stillness, even though it isn't. And deeper still, far beneath oceans and mountains, the core waits in darkness, revealed not by light, but by the way waves bend, vanish, and return. From far above, Earth looks finished, a polished sphere, a calm system, but inside, it's layered like a long, slow history written in pressure. And the way we learn those layers exists is almost delicate, not by drilling, not by seeing, but by noticing where the planet's vibrations fail to arrive, the place where the mantle ends. Once seismologists accepted the idea of boundaries, places where rock properties change abruptly, the next question became unavoidable. Where does the mantle end? Because the mantle is enormous. It reaches down for roughly 2,900 kilometers, about 1,800 miles beneath the crust. That is most of Earth's volume. And yet, the mantle is still rock, in the sense that it can carry both P waves and S waves. It's hot, it's slow-moving over geologic time. But to seismic waves fast, sudden disturbances, it behaves as a solid. So if S waves vanish beyond certain distances, something deeper must be different. That something is the core. By studying the exact angles where wave arrivals disappear, and where P waves behave strangely, slowing down and bending sharply, scientists identified a major boundary at about 2,900 kilometers down. This boundary is called the Gutenberg discontinuity, named after the seismologist Benno Gutenberg. It marks the transition between the solid mantle and the liquid outer core. From space, it's hard to emotionally grasp what that means. A liquid layer nearly the size of a planet, hidden under solid rock. A sea of molten iron alloy, not near the surface where it would glow red, but deep enough that pressure turns molten into something far more intense, dense, heavy, and restless. Why S waves disappear? The key is still the simplest fact in the whole story. P waves can travel through solids and liquids. S waves can travel only through solids. So when S waves stop showing up on seismographs beyond a certain range, it's not a mystery anymore. It's a signature. The planet is telling you there is a liquid layer down there, and that liquid layer is large enough to cast a global shadow. It's one of the strangest kinds of proof humans ever accepted. Learning what exists by mapping what doesn't arrive. The quiet return of impossible waves. Then, in the 1,930 seconds, something even subtler appeared in the records. Seismologists noticed faint P-wave arrivals in regions where, in the simplest models, there should have been a kind of silence. Not the main P-wave, not the direct path, but small signals, late, delicate, easy to miss, arriving like an echo. In 1936, the Danish seismologist Inge Lehmann proposed an explanation that was both bold and beautifully restrained. Inside the liquid outer core, there must be another boundary, and inside that boundary, a solid inner core. In other words, Earth's core is not just a core, it's two cores. A liquid outer core where S waves can't go, a solid inner core revealed by reflected and refracted P waves that behave differently once they encounter that deeper, denser center. This inner boundary is often called the Lehman discontinuity, and it sits at roughly 5,150 kilometers down, about 3,200 miles beneath your feet. If you like numbers that help you feel scale, Earth's radius is about 6,371 kilometers, 3,959 miles. The mantle ends around 2,900 kilometers down. The outer core extends from there down to about 5,150 kilometers. The inner core occupies the deepest region, with a radius of roughly 1,220 kilometers, about 760 miles. So the solid inner core is not small. It's roughly the size of Pluto, but compared to the whole planet, it's a hidden seed at the center, dense, hot, and under pressures that make ordinary language feel too light. A planet used as its own experiment. One reason this science advanced so quickly in the 20th century is that earthquakes happen repeatedly all over the world, at many depths and strengths. They provide endless test signals. But there's another reason the models sharpened over time. Humans created signals too. Not gently, unfortunately, not gently at all, but clearly. In the mid-20th century, large controlled explosions, including nuclear tests, produced seismic waves with known locations and known timing. That made them, from a purely scientific standpoint, clean sources. You knew exactly when and where the wave began. Seismologists could compare those recordings with earthquake recordings and refine the planet's internal map. And later, monitoring efforts connected to arms control pushed seismic technology even further, building better instruments, better global coverage, and more precise ways to read the smallest arrivals in noisy data. In the US, this long arc of research is one reason modern seismic networks became so capable, not just for studying Earth's interior, but for hazard monitoring and early warning systems in certain regions. So there's a strange dual story here. Earth's internal structure was revealed partly by natural catastrophe and partly by humanity's ability to shake the ground on purpose. The calm picture that emerges. If we float quietly above the night side of the planet, it's tempting to imagine the interior as a neat cutaway diagram. But the real Earth is not a clean drawing. It's a living object. The crust is thin and brittle, fractured into plates. The mantle is solid but slowly convecting, carrying heat upward over deep time. The outer core is liquid metal in motion, one of the reasons Earth can generate a magnetic field. And the inner core is solid, compressed beyond ordinary intuition, enduring as the densest center. All of this was learned without touching those depths, because when Earth is struck by tectonic slip, by rupture, by sudden release, its waves become a kind of language, a language made of timing, a language made of shadows, and once you learn how to listen, the planet begins to describe itself. In the next part, we'll slow down and make the core feel more real, not just as a liquid layer, but as an engine. We'll talk about how the core's motion connects to Earth's magnetic field, and why we can say with confidence that there is no giant permanent magnet buried inside. Just a moving sea of metal, generating an invisible shield that reaches out into space. From our quiet vantage point in space, Earth does something that feels almost personal. It holds its ground, not just with gravity, but with an invisible structure that wraps the planet like a soft, protective contour. The magnetic field. You can't see it in ordinary light, but you can see its fingerprints. You can see them in the aurora, those slow green and purple curtains over Alaska, over northern Canada, sometimes dipping far enough south that people in the northern U.S. step outside and suddenly realize the sky is doing something ancient. And you can measure it directly, with instruments on the ground, on aircraft, and on satellites that glide above the atmosphere, and map Earth's magnetism the way a surveyor maps hills and valleys. So if we're asking, how do we know what's inside Earth? This is one of the most elegant answers. Because the inside of Earth reaches outward, it leaves a signature in space. Why a giant permanent magnet doesn't work. It's tempting to imagine Earth as a big bar magnet, a solid chunk of metal with north and south baked in forever. But physics doesn't let that story hold. Most permanent magnets lose their stable magnetism when they get too hot. There's a threshold called the Curie temperature, the temperature at which magnetic minerals stop behaving like permanent magnets. For iron, it's around 770 degrees Celsius, about 1,420 degrees Fahrenheit, and deep Earth temperatures are far above that. The core is not just warm, it's extreme thousands of degrees. So, if someone asks, is there a giant permanent magnet inside Earth? The calm answer is no, because the core is far too hot for permanent magnetism to survive. So what's left? Only one option that fits the measurements. Earth's magnetism has to be generated continuously, in real time like a living process. The geodynamo, a slow ocean of metal, deep beneath the mantle, inside the liquid outer core, iron-rich metal is moving, not sloshing like water in a glass, nothing that quick. More like deep convection, slow circulation driven by heat escaping from the core, and by subtle chemical changes as Earth cools. And when an electrically conductive fluid moves, it can generate magnetic fields. This is called a dynamo. So Earth's magnetic field is not a fossil, it's not a relic, it's not something that was installed long ago. It's something Earth is doing, a planet-sized engine, turning motion into magnetism. From space, that magnetism shapes a region around Earth called the magnetosphere, a protective bubble that deflects much of the solar wind. It doesn't block everything, and it doesn't make us invulnerable, but it matters. It's part of why the space around Earth is gentler than it would otherwise be. And this is one of the key indirect clues about Earth's interior. A long-lived magnetic field strongly suggests a liquid, moving, conductive layer inside the planet, which is exactly what seismology tells us too. Different methods, same story. Earth's magnetic field changes, and that's evidence. Here's another quiet detail that strengthens the case. Earth's magnetic field is not perfectly stable. It drifts, it reshapes, it weakens in some regions and strengthens in others. The magnetic North Pole is not nailed in place, it migrates over time. This kind of behavior makes sense if the field is being generated by motion in a liquid layer. It's like watching ripples on the surface of a lake and realizing the water below is moving. And those changes aren't just measured by scientists somewhere. In the US, organizations like the USGS and NOAA help publish magnetic models used for navigation and mapping because magnetic variation matters for compasses, aircraft systems, and many practical tools that still care about Earth's field. So even in everyday life, the magnetic field is not theoretical. It's part of infrastructure, part of the planet's operating system. Another clue: gravity, mass, and balance. Now, while we're still hovering above the planet, there's another quiet way Earth tells us about its inside: gravity. Earth's gravitational field isn't perfectly uniform. It varies slightly from place to place because mass isn't distributed perfectly. Evenly mountain ranges, ocean trenches, dense rock provinces, mantle structure. Modern satellites have mapped these variations with extraordinary precision. And even without going into the technical details, the big idea is simple. If you can measure Earth's mass and the way gravity behaves around it, you can constrain how dense Earth must be inside. Earth's average density is about 5.5 grams per cubic centimeter, which is much denser than surface rock. The crust and mantle are mostly silicate rock. Silicates are not dense enough to make Earth that heavy unless something denser is concentrated deep inside. So gravity pushes us toward the same conclusion seismology pushes us toward. There must be a metal-rich core, a dense center, a deeper heart. And when scientists combine gravity measurements with Earth's rotation behavior, how the planet wobbles, how its moment of inertia works out, the model that fits best is a layered Earth with a dense core and a thick rocky mantle. Again, different methods, converging answer. Where composition comes from, rocks, fragments, and visitors from space, seismology gives us structure, where boundaries are, what's solid, what's liquid. But composition, what the layers are made of, comes from a wider set of clues. Some are familiar. We can sample the crust directly. We can drill into it, collect rock cores, and analyze them with chemistry that's routine in modern geology. And even though drilling doesn't reach the mantle, Earth sometimes delivers mantle material upward for us. Volcanic eruptions can carry fragments from deep below, especially certain kinds of volcanic pipes that rise quickly. Geologists study mantle-derived rocks and inclusions, pieces of deeper material that hitch a ride upward before they can melt completely or transform. It's like the planet occasionally drops a sealed envelope on the surface. Not the whole message, but enough to confirm the handwriting. And then there are meteorites. This is an underappreciated bridge between astronomy and geology, something that tends to land well with an American audience because it ties Earth science to space exploration in a very direct way. Some meteorites are rocky and silicate-rich. Some are iron-rich. Some are mixtures. They're not perfect replicas of Earth's interior, but they are physical evidence of early solar system materials, what solid bodies were made from before planets fully differentiated. When you combine that with basic physics, heavy elements sinking, lighter ones rising in a molten early planet, you get a coherent picture, silicate-rich layers becoming mantle and crust. iron and nickel concentrating into the core. It's not guesswork. It's the simplest outcome of gravity acting on a hot, forming world. The calm conclusion of this section. So, even before we return to earthquakes and wave paths, we already have a strong, layered argument. Seismology tells us where the liquid layer is and where a solid inner core exists. Magnetism tells us a conductive fluid is moving deep inside, powering a dynamo. Gravity and Earth's average density tell us the planet must contain a dense metallic center. Rocks and meteorites support the chemistry of that model and explain how Earth could separate into layers. This is what science often looks like when it's working well. Not one perfect proof, but many partial proofs that overlap like transparent maps until the shared shape becomes hard to deny. In the next part, we'll return to the seismic story and make it feel more tangible. How scientists use arrival times minute differences recorded across continents to turn earthquakes into a scanning system. Not a scanner we built, a scanner Earth provides every time it shifts and releases its stored strain. And from that, we'll build the most reassuring idea of all. You don't have to drill to the core to understand it. You only have to learn how to listen. From orbit, an earthquake is invisible. You don't see a crack rip across the globe. You don't see the ground lurch. Earth looks the same, blue, calm, quietly rotating. And yet, in that moment, the planet becomes something else, a ringing object, a bell struck deep inside, not with sound that travels through air, but with vibrations that travel through rock. And those vibrations do something extraordinary for science. They turn Earth into its own scanning machine. Not a scanner we built. A scanner the planet generates on its own whenever stress releases along a fault and the crust shifts by inches or by meters. The global listening network. Across the United States and across the world, there are thousands of seismometers, sensitive instruments that detect ground motion far smaller than anything we could feel. In the U.S., networks coordinated through groups like the USGS, university labs, and large research efforts have made the planet feel, in a way, wired. In the last couple of decades, one of the most famous American projects was EarthScope, a campaign that placed a rolling curtain of seismometers across the country, often called US Array, to map what's happening beneath North America. If that sounds abstract, picture it like this. Imagine you're trying to understand the shape of something hidden, something you can't touch. So you place microphones everywhere and you wait for natural impacts to happen. Then you compare what each microphone heard and when it heard it. That, in essence, is modern seismology. Earthquakes provide the impacts. Seismometers provide the listening. Time and geometry provide the map. Two messengers, P waves and S waves. When an earthquake happens, the energy doesn't spread in one single kind of wave. It spreads in different modes, different styles of motion. The two most important for understanding Earth's interior are the body waves, P waves, primary waves, and S waves, secondary waves. P waves are compressional. They squeeze and release material in the same direction they travel, like a slinky being pushed and pulled. They are the fastest seismic waves. so they arrive first. And crucially, P waves can travel through solids and liquids. S waves are shear waves. They move material side to side, perpendicular to the direction of travel like a rope being flicked. They arrive later. And crucially, S waves cannot travel through liquids. This one fact, quiet, almost simple, is one of the sharpest knives we have for cutting Earth into layers. Because if S waves vanish beyond a certain point, it means they ran into something liquid, not maybe liquid. Liquid in a way that matters physically. Arrival times, the most patient kind of evidence. A seismometer's record, a seismogram, looks like a calm line, then a sudden trembling, then a more complex shaking. And in that pattern, the first clean arrival is typically the P wave. The next is the S wave. When an earthquake occurs, seismometers at different distances record these arrivals at different times. Close stations see them quickly. Distant stations see them later. Now here's the key. If Earth were uniform inside, same material, same density, no layers, then the relationship between distance and arrival time would be simple and smooth. But Earth is not uniform. Density increases with depth. Material changes. At certain depths, composition and state change sharply. So the waves don't just travel in straight lines. They bend, they refract, they reflect. They speed up in some layers and slow down in others. And that bending, when mapped carefully, reveals structure the way a medical scan reveals organs. Refraction. Why the rays curve? From space, we can imagine a simplified Earth, a layered sphere. Seismic waves travel faster in denser, more rigid material. As a wave dives deeper, it often enters material where it can move faster, so the ray path curves, gradually bending back upward. This is why seismic diagrams often show graceful arcs instead of straight lines. It's not artistic, it's physics. It's the same basic logic as light bending when it moves between air and water, except here the medium is rock, and the bending happens over thousands of kilometers. The first great boundary, the moho. Early in the 20th century, scientists noticed something unexpected. At certain distances from an earthquake, some waves arrived earlier than they should have. Not by a little, by enough to demand an explanation. The best explanation was that the waves were diving down, hitting a deeper layer where wave speed was higher, then refracting and returning to the surface like a shortcut through faster material. That discovery revealed a boundary between the crust and the mantle, the Mohorovičić discontinuity, usually shortened to the moho. It's one of those discoveries that feels almost poetic. We couldn't drill to the mantle, so Earth told us it was there by letting waves run through it and come back faster than expected. And once you can find the moho, you can measure crust thickness, which is why we know the crust is thin under oceans, thicker under continents without ever slicing Earth open. A far deeper boundary, the shadow zones. Now we go deeper down toward the core. This is where the planet's scan becomes even more dramatic. If you map where seismometers do and don't detect certain waves after a large earthquake, you find something strange. There are regions on Earth's surface where S waves never arrive from a given quake. A silent arc, a missing signal. This is called an S-wave shadow zone. And because S-waves can't pass through liquid, the conclusion is unavoidable. Somewhere inside Earth, there is a liquid layer large enough to block shear waves entirely. That liquid layer is the outer core. P-waves behave differently. They can pass through liquids, but they slow down and bend sharply when they enter a liquid region, creating their own shadow zone, a band where direct P-waves don't arrive as expected. When you combine the P-wave behavior and the S-wave disappearance, the geometry points to a boundary around 2,900 kilometers deep, the core mantle boundary, also called the Gutenberg discontinuity. This is one of the most important moments in the whole story, because it's not a subtle inference, it's a planet-sized demonstration. A wave that should be there is missing. A different wave that should arrive on one path arrives on another. The only model that fits is a layered Earth with a rocky mantle and a liquid outer core, and then one more hidden layer inside the liquid. For a while, that might have felt like the end of the map. Crust, mantle, liquid core. But the planet had another detail to reveal. In the 1,930 seconds, scientists noticed faint P-wave arrivals appearing in places they weren't supposed to, signals inside the P-wave shadow zone. Not strong signals, more like whispers. And those whispers were best explained if some P-waves were reflecting and refracting off a solid inner core inside the liquid outer core. That discovery is associated with the seismologist Inga Lehmann, and the boundary between the outer core and inner core is often called the Lehmann discontinuity. So the core itself has structure, a liquid outer core and a solid inner core. And the reason a solid core can exist inside a liquid one comes down to pressure. Deep enough, pressure becomes so immense that it can force iron-rich material into a solid state, even at extreme temperatures. A quiet pause. What we've actually done, without drilling, without cameras, without bringing samples from 3,000 kilometers down, we have still traced Earth's internal architecture. We did it by listening, by measuring arrival times, by charting what disappears, by noticing what bends and what reflects, and by repeating it across thousands of earthquakes with thousands of instruments until the patterns stopped being maybe and became geometry. In the next part, we'll go one step more concrete. We'll connect these wave behaviors to what the interior is made of, not just where the layers are, but why iron belongs in the core, why silicates dominate the mantle, and how meteorites and high-pressure experiments help complete the picture. Still from orbit, still calm, still listening to a planet that every so often tells us what it is by the way it rings. From far above the atmosphere, Earth doesn't look like a layered world. It looks like a single living surface, clouds moving, oceans breathing, continents holding their quiet shape. But seismology has already given us a kind of internal outline. Crust, mantle, liquid outer core, solid inner core. The next question is softer, but in some ways even more intimate. If those layers are real, what are they made of? Because a boundary is one thing, a composition is another. And here, the story becomes a mosaic, many different kinds of evidence, none of them perfect on their own, but together forming something sturdy enough to trust. Meteorites. Pieces of the same beginning. One of the most calming ideas in planetary science is also one of the most powerful. Earth is not unique material. It formed from the same early solar system debris as everything else: dust, rock, metal, ice, swirling in the protoplanetary disk around the young Sunday. And some pieces of that early material still arrive at Earth, not as a theory, as objects you can hold. Meteorites are, in a sense, time capsules, fragments that never became full planets, or fragments knocked loose from larger bodies and preserved in cold space for billions of years. When scientists analyze meteorites, they find a clear pattern that maps beautifully onto Earth's internal structure. Stony meteorites, rich in silicate minerals, resemble what we see in Earth's crust and mantle. Iron meteorites, dense and metallic, resemble what we infer for Earth's core, especially iron, with nickel mixed in. And there are stony iron meteorites, mixed types, that remind us that early planetary material began as a chaotic blend before it separated. That last part matters, because it connects to the central mechanism that builds layers in a planet. Differentiation. Why heavy things sink in a hot young planet. Early Earth was not the cool, stable world we know. It was hotter, more molten, more violent, a place shaped by impacts and internal heat. In a world like that, gravity becomes a sorting machine. Heavy elements, iron and nickel, tend to sink. Lighter silicate material tends to rise, not instantly and not neatly. But over time, the planet separates into layers in the same way a stirred mixture slowly settles into order. So meteorites don't prove Earth is layered. Seismology already did that. Meteorites help explain why those layers are made of the substances we think they are. They show us the kinds of raw ingredients available at the beginning. And they show us that iron-rich and silicate-rich bodies are both common outcomes of planetary formation. Volcanic and mantle rocks. Messages carried upward. If meteorites are messages from outside, volcanic rocks are messages from below. Not from the deep core. Nothing rises from 3,000 kilometers down like a letter from the abyss. But from the mantle and upper mantle, Earth does sometimes send material upward through volcanic processes. Certain rock types, like mantle-derived xenoliths, chunks carried up in volcanic eruptions, can preserve a sample of what lies beneath the crust. These aren't perfect samples of the mantle at large, but they anchor the picture in reality. They say, yes, below the crust, Earth's interior is dominated by silicate minerals under high pressure, not speculation. Actual material, altered by the journey, but still recognizable as deep origin rock. This is part of why the mantle is described the way it is: largely silicate, dense, hot, solid, on short time scales, and slowly flowing on long ones. Gravity. The planet's mass distribution written in orbit. From space, gravity is not an abstract thing. It is the shape of motion. Satellites don't simply circle Earth. They respond to tiny variations in Earth's gravitational field, subtle changes caused by how mass is distributed inside and on the surface. Over the past few decades, satellite missions, including well-known NASA efforts, have mapped Earth's gravity field with remarkable precision. And that gravity field is not uniform. It has bumps and dips, patterns that reflect mountain ranges, ocean trenches, variations in crust thickness, and deeper structures in the mantle. Gravity mapping doesn't draw a clean cross-section the way a textbook diagram does. It gives something more realistic, a living, shifting field that implies density differences and confirms, at a planetary scale, that Earth cannot be a uniform ball. And when gravity data is combined with seismic models, the picture tightens. Different methods begin to agree, and agreement in science is a kind of quiet comfort. Earth's magnetic field, evidence of a moving metallic core. Now, from orbit, the magnetic field is one of the most beautiful, invisible things Earth carries. It reaches out into space, forming the magnetosphere, an elegant protective shape that turns the solar wind aside and guides charged particles toward the poles, where they paint auroras. The key question is, where does that field come from? It is tempting on a human level to imagine a giant permanent magnet inside the planet, but the physics refuses that comfort. At core temperatures, permanent magnetism doesn't survive. Above a certain threshold, often called the Curie temperature, magnetic domains in solid materials lose the stable alignment that creates permanent magnet behavior. So Earth's field must be generated another way. The best explanation is the geodynamo, a vast, slowly churning ocean of electrically conducting fluid, liquid iron alloy in the outer core, moving under the influence of rotation and heat flow. A moving conductor can generate magnetic fields. A rotating planet can organize that motion into patterns. And the result is a magnetic field that is strong, global, and restless, shifting over decades, wandering, sometimes weakening, sometimes strengthening, and occasionally flipping polarity over long timescales. We don't see the outer core, but the magnetic field is a signature of something like it, a liquid, metallic, convecting region deep inside the planet, and again, it matches what seismology already told us. Different lines of evidence converge on the same structure: high-pressure experiments. Building Earth's interior in miniature. There's another kind of evidence that doesn't come from observation at all, but from recreation. In laboratories, scientists can compress tiny samples of minerals and metals under extreme pressures and temperatures. They use devices like diamond anvil cells and other high-pressure techniques to mimic conditions found deep inside Earth. These experiments answer questions like, how do silicate minerals behave under mantle pressures? What phases do they transform into? How fast do seismic waves travel through them? How does iron behave at core pressures? Under what conditions can an iron-rich inner core be solid while an outer core stays liquid? This is not a perfect simulation of a planet. It's a controlled, simplified version of the physics. But it's another bridge between inference and reality. Because when lab measurements of wave speeds match the wave speeds inferred by seismology, the interpretation becomes stronger. And when high-pressure mineral phases match what we expect at certain depths, the layered model becomes not just plausible, but physically coherent. Models, not guesses, but constrained stories. Finally, there are computer models, mathematical descriptions that tie everything together. Seismic data, gravity, magnetism, mineral physics. thermodynamics, planetary formation. A model isn't a fantasy. It's a story with handcuffs on. If it contradicts seismology, it fails. If it can't reproduce Earth's mass and moment of inertia, it fails. If it can't produce a magnetic field consistent with observations, it fails. If it predicts wave speeds that don't match real seismograms, it fails. And because Earth has been observed in so many independent ways, the successful models are those that respect a dense web of constraints, which is why the modern picture crust, silicate mantle, liquid iron-rich outer core, solid iron-rich inner core is not held up by one fragile argument. It's held up by many. A gentle summary from orbit. So, if we drift here for a moment, watching the planet rotate, watching the night side glow with city lights, watching the auroral oval brighten and fade, we can let the central idea settle. We know what's inside Earth the way we know what's inside a body with medical imaging, not by opening it, but by sending waves through it, by measuring fields around it, by studying fragments that share its origin, by recreating its conditions in labs, and by building models that survive the pressure of real data. In the next part, we'll pull these threads into a single, calm timeline. From the first seismic clues, to the discovery of the moho, to the shadow zones, to the inner core, and then to the modern era of dense sensor networks and satellite measurements. A slow, steady story of how a planet that seems unreachable beneath our feet becomes, step by step, knowable. From orbit, Earth looks finished, a complete sphere, a polished system. But the science of Earth's interior did not arrive as a single revelation. It arrived the way most reliable knowledge arrives, slowly, through many small confirmations, through patient disagreement with the simplest assumptions. So let's trace the story gently, like following a faint trail across snow, not a list of dates to memorize, more like a sequence of moments where the planet quietly gave up another secret. The earliest clue: waves that behave differently in different materials. Once seismographs existed and networks began to spread, scientists could do something that feels almost magical. They could compare the same earthquake recorded at many locations, and when they did, they noticed patterns that didn't match a uniform Earth. Some waves arrived early at certain distances, some arrived late, some didn't arrive at all. The first sleepy insight here is simple. If Earth were the same material everywhere, waves would behave the same everywhere, but they didn't. So Earth wasn't uniform. 2. The moho, the first sharp boundary, crust versus mantle. In 1909, Andrija Mohorovičić studied seismic records and noticed something that didn't fit the smoothly increasing density idea. At certain distances, waves arrived faster than expected, as if they had found a shortcut, but not a geometric shortcut, a physical one. The only way to explain the timing was that some waves traveled down, hit a boundary, and then traveled through a deeper layer where seismic waves moved faster. That implied a sharp change in material properties, and that boundary became famous. The Mohorovičić discontinuity, the moho. Not an abstract concept, a real transition in Earth, a place where the crust ends and mantle begins. from space that might feel like a small detail, but it was a turning point because it proved Earth had distinct layers, not just gradual change. Shadow zones. The moment Earth's core became unavoidable. After the moho, the next big leap came from something that at first looked like a problem. At certain angles, certain distances from an earthquake, seismographs stopped recording some types of waves. In particular, S waves disappeared past a certain range. P waves bent and left a quiet zone. This wasn't subtle, it was dramatic, and it carried a profound meaning: the S-wave shadow zone. S-waves can't move through liquid, so if S-waves vanish beyond a certain path through Earth, something deep inside must be liquid. That was one of the strongest pieces of evidence for a liquid outer core. The P-wave shadow zone. P-waves can travel through liquid, but they slow down and refract differently in it. So P-waves didn't vanish entirely, but they bent in a way that created a region with no direct arrivals. That shape wasn't random. It pointed to a boundary where wave speeds changed sharply, another clear internal interface. This boundary is now known as the Gutenberg discontinuity, the mantle outer core boundary, about 2,900 kilometers deep. At that point, Earth was no longer just crust and mantle. It had a metallic heart, the inner core, a solid center discovered by faint arrivals. If the outer core is liquid, what about the center? For a while, Earth's core was imagined as fully liquid, but in 1936, Ing Lehman noticed something unexpected: very faint P-wave signals appearing where, according to earlier models, they shouldn't. The most elegant explanation was that some waves were being refracted and reflected by a solid region inside the liquid core. So the core wasn't one uniform layer. It had structure, a solid center inside a liquid ocean. This gave us the Lehman discontinuity, the boundary between the liquid outer core and solid inner core. And that completed the most famous basic outline: crust, mantle, liquid outer core, solid inner core. Not because anyone drilled there, because the planet itself provided the data every time it shook. 5. The modern era. Earth listened to itself with a global nervous system. In the decades that followed, the story became less about singular discoveries and more about refinement. The world built denser networks, more seismometers, better timing, including GPS synchronized clocks, cleaner signal processing, better global cooperation and data sharing. Earth became surrounded by sensors, like a planet wearing a stethoscope. Modern seismology doesn't just locate earthquakes. It maps subtle variations in wave speed that can suggest cold, sinking slabs in subduction zones, hot, upwelling mantle plumes, differences in crust thickness, large-scale mantle structures that look like slow-moving currents frozen into rock. Not perfect snapshots, but enough to see Earth's interior as dynamic, not static. Satellites joined the picture. Gravity and magnetism from above. While seismology listens from the surface, satellites let us measure from space. Gravity mapping. Earth's gravity field isn't perfectly smooth. Satellites detect tiny deviations caused by mountain belts, ocean trenches, variations in crust density, deep mantle structure. This reinforces the idea that Earth is layered and uneven in detail. Magnetic field measurements. Space-based observations show the magnetic field changing over time, drifting, weakening in some regions, strengthening in others. That behavior strongly supports the idea of a fluid, convecting, conducting outer core powering a geodynamo. Again, no direct view, but the signature is unmistakable. A quiet principle. Independent methods converge. And this is the most important American science framing to land gently. We don't rely on one heroic measurement. We rely on convergence. Seismology suggests layers. Gravity suggests density structure. Magnetism suggests a moving conductor deep inside. Meteorites suggest likely compositions. High-pressure labs confirm which materials behave like the seismic data says they must. When different tools built on different physics agree on the same interior structure, that agreement becomes the real evidence. A soft landing thought. So, if you ever find yourself thinking, how can we possibly know what's inside Earth? You can answer quietly. We know it the same way we know the inside of many things we can't open. By how they respond to waves, by how they shape the fields around them, by how their mass reveals itself through motion. Earth can't hide its interior completely, because its interior affects everything, even from orbit. From orbit, Earth looks like a finished thing, a complete sphere, turning in silence. White weather spirals over blue oceans. Thin clouds blur the coastline. City lights glow faintly on the night side, like tiny constellations stitched onto the surface. And if you stay up here long enough, floating above the planet, one question starts to feel almost impossible. How can anyone claim to know what's inside that world? Because from this distance, Earth doesn't reveal its interior at all. It keeps its secrets under rock, under ocean, under thousands of kilometers of pressure. And yet, we do know. Not perfectly. Not with the certainty of opening a box and looking inside, but with the kind of confidence that comes from patterns repeatable, measurable patterns that only make sense if Earth is layered. So tonight, let's do something gentle. Let's descend. Not like a drill, not like a machine forcing its way downward, but like a calm, imagined glide guided by evidence, guided by the way Earth moves and rings and bends the invisible waves that travel through it. The skin of the planet, crust. As we begin to drift downward, Earth's surface grows larger beneath us. Continents become textured. Mountain ranges rise like wrinkles in a slow, ancient fabric. Oceans so wide from space start to look thin compared to the solid planet below them, and the first layer we touch is the one we live on. The crust. It feels thick to us because it's our entire world, our cities, our roads, our forests, our stories. But in planetary terms, the crust is a skin, a film, a shell. On the ocean floor, it's usually only a few miles thick. On continents, it can be thicker tens of miles in some regions. If Earth were the size of a classroom globe, the crust would be thinner than the paint. And that fact alone explains why drilling can never solve this mystery. The deepest humans have ever drilled into Earth is around 12 kilometers, about 7.5 miles. Impressive in human terms, but compared to Earth's radius, almost nothing. A scratch, a careful scratch, but still a scratch. So the real question becomes, if we can't dig deep, what else can we do? And the answer is, we listen. 2. The first boundary, the moho. As we sink through the crust, we reach a transition zone, not visible, not obvious, but real, a place where the rock changes, where seismic waves change speed. This boundary is called the Mohorovičić discontinuity, the moho. It's the line not drawn in ink, but traced in timing. When earthquakes happen, waves travel through Earth, and the time they take to reach seismometers doesn't match a uniform crust. Some waves arrive too quickly at certain distances, meaning they must have traveled through deeper, faster material. That deeper, faster material is the mantle. So the moho is not a guess. It's the first strong confirmation that Earth is layered, a boundary revealed by waves, a quiet, invisible shoreline inside the planet. The mantle, a world of rock that flows like time. Now we enter the mantle. From space, it's impossible to imagine the mantle because we think in surface terms. We think rock means stillness. But the mantle is rock under pressure and heat so intense that over long spans of time it behaves like something else. Not liquid like water, not brittle like stone in your hand. Something in between, solid in the short term, flowing in the long term. Slow convection, a planet-sized circulation. The mantle is thick, nearly 3,000 kilometers deep, and in that depth, pressure rises and the properties of rock change gradually. Seismic waves speed up in some regions, slow down in others, not because the mantle is uniform, but because it has structure. Colder, denser slabs sinking beneath subduction zones, warmer upwellings rising in plumes, boundaries where minerals change form under pressure. This is where modern Earth science becomes almost poetic. You can't see the mantle, but you can map how it bends waves, and those bends are like brush strokes in an invisible painting. 4. The moment the planet surprises you, the core boundary. Now we approach a depth where the old idea of more rock, just hotter, stops working. Earth does something strange here. Not emotionally strange, physically strange. At around 2,900 kilometers down, seismic data shows a dramatic shift. The waves behave as if they've entered a different kind of medium. And this is where Earth reveals one of its most important facts. The mantle ends, the core begins. This boundary is called the Gutenberg discontinuity, and it was not found by drilling. It was found by noticing what disappears, the S-wave silence. S-waves cannot travel through liquid, so when seismologists saw that S-waves vanish beyond certain angles, creating what's called an S-wave shadow zone, they understood something deep inside Earth must be liquid. That something is the outer core, a liquid layer, mostly iron, with lighter elements mixed in, a global ocean of metal, not calm, not still, moving, circulating, because it has to. 5. The outer core, the engine of the magnetic field. If we could drift into the outer core, we wouldn't see lava, It's not molten rock, it's molten metal, iron-rich fluid under crushing pressure, and this is where Earth's magnetic field is born. From space, you can measure Earth's magnetism, you can see its shape, you can track how it shifts and drifts over time. The fact that it changes is part of the clue. A permanent magnet would not behave this way, and a permanent magnet couldn't survive those temperatures anyway. So, the best explanation, the one supported by physics and observation, is a geodynamo, conducting fluid moving under rotation, generating magnetic fields. The outer core is not just a layer, it's a machine, a natural engine powered by heat and motion, and it creates a protective bubble around the planet, deflecting charged particles from the sun, shaping auroras, helping Earth stay hospitable over long timescales. From orbit, that field is invisible, but it's one of the most important parts of your life. Even if you never think about it. Another surprise: the inner core. For a while, scientists imagined Earth's core as fully liquid. It would have been a reasonable guess, but Earth isn't content with simple models. In 1936, a seismologist named Inge Lehmann noticed faint signals in places where P waves shouldn't have been. Not loud signals, not obvious ones. The kind you only see if you look carefully, and you trust your instruments, and you take the time to ask, why is anything arriving here at all? The best explanation was a solid inner core, a dense center inside the liquid, like a sphere of metal locked in a sea of metal. This boundary is now called the Lehmann discontinuity, and it gives us the complete basic architecture: crust, mantle, liquid outer core, solid inner core. Again, not from a hole in the ground, from waves, from timing, from the planet's own vibrations. The deeper truth we know because different evidence agrees. Now, as we hover in imagination near the center, it's worth stating the calmest and most important principle. We don't know Earth's interior because of one trick. We know it because independent methods converge. Seismic waves map boundaries. Gravity measurements map density. Magnetic field measurements map the behavior of a moving conductor. Meteorites suggest what Earth's building blocks were like. Laboratory experiments under extreme pressure confirm how materials behave. Computer models test whether the physics holds together. And when all of those different tools agree, the picture becomes stable, not perfect, but reliable, returning gently, the planet as a readable object. So, when someone asks, how do we know what's inside Earth? The calm answer is, because Earth is not silent. It rings, it bends waves, it shapes fields. It reveals its mass through gravity. It shows its magnetism through space. Even when we can't reach the depths directly, we can still measure the consequences of those depths. And those consequences, when carefully studied, tell us what's inside. A soft closing image. From orbit, Earth looks like a calm marble, but inside, it is layered, alive with motion, quietly circulating heat through rock and metal, a world that has been cooling for billions of years and is still, even now, releasing its warmth, still turning, still shielding itself, still generating a magnetic field, still shaking occasionally, reminding us that the interior is real. and active and powerful. And the remarkable part is this: we learned all of it without opening the planet. We learned it by listening. From this high distance, Earth still looks peaceful, a bright curve, a thin atmosphere, a planet that seems finished. But now the image carries a second layer, an understanding that the calm surface is only the last, visible page of a much thicker story. Beneath the oceans and continents, beneath the mountains and deserts, there are boundaries that matter, not because we've touched them with drills, because the planet keeps giving itself away, in vibrations, in gravity, in magnetism, in patterns that repeat often enough to become trustworthy. And if the goal of this episode is one clear idea, it's this: we know what's inside Earth, the same way we know what's inside the sun, or a distant star, or a moon we can't dig into. We learn by watching what moves through it, by measuring what bends, by listening to what echoes back. Earth is wired with listeners. Down on the surface quietly, all over the world, seismometers wait. They don't look dramatic. They're small, patient devices, recording the motion of the ground with a kind of constant attention. Most days, they capture almost nothing your body would notice. But when Earth shifts, when a fault slips, when a plate releases stress, those sensors become part of a global instrument. And in the United States, that instrument is especially dense. Across California, Alaska, the Pacific Northwest, the Intermountain West, and the Central States, networks of stations keep watch. Some exist for hazard monitoring because earthquakes matter for infrastructure and safety. Others exist for science because the most accurate map of Earth's interior comes from many measurements, gathered over time from many angles. This is one of the more comforting truths about modern geology. Even though the planet is vast, the data is local. A quiet sensor on a hillside in California can help interpret an earthquake in Japan. A station in the Midwest can help map the core's boundary using waves born in the South Pacific. The Earth is round, and the waves don't care about borders. They travel, they curve, they refract. They carry information through the interior like messages in a language made of pressure. The American landscape as a living laboratory. From orbit, the United States has its own patterns: coastlines, deserts, mountain chains, snowfields. From below the surface, it has another pattern: tectonic tension. Alaska sits near one of the most active plate boundaries on the planet. It's a place where oceanic crust dives beneath the continent, building stress and releasing it in frequent earthquakes. It's also a place where seismic data is extraordinarily valuable because big earthquakes generate waves strong enough to illuminate deep earth structures all over the globe. California is defined by the long, complicated relationship between the Pacific Plate and the North American Plate. Faults there don't only create hazards, they create data. Over decades of observation, that data has helped refine how we understand wave speeds in crust and mantle, how faults behave, and how the upper layers of Earth are stitched together. The Pacific Northwest holds a different kind of tension subduction offshore, a quiet but enormous tectonic system capable of major events. Even when it's calm, the region is watched closely, not because fear is helpful, but because readiness is. And then there is Yellowstone, not as a doomsday headline, but as a steady reminder of what heat can do to rock. The park's geysers and hot springs are surface expressions of a deeper system. The U.S. monitors Yellowstone continuously, not because it's an imminent catastrophe, but because it is an active geological environment where careful measurement matters. In a strange way, the United States is full of places where the planet's interior becomes easier to study, not because the Earth is kinder here, but because the signals are strong and the instrumentation is dense, and the research culture is persistent. Gravity, the planet's mass written in motion. Seismology tells us about boundaries and physical states, solid versus liquid, layered transitions, changes in composition. But gravity adds another kind of clarity. From space, gravity is not abstract, it is measurable. Satellites can detect tiny differences in Earth's gravitational pull from place to place. Those differences reflect mass distribution, where rock is denser, where the crust is thick, where large mountain ranges sit, where ocean trenches carve deep into the planet's surface. Gravity doesn't tell you a crisp picture of the core the way seismic waves do, but it provides a constraint, like a signature on the bottom of a document. Whatever is inside Earth must add up to the mass we measure. Whatever layers we propose must produce the gravitational field we observe. When the gravity data and the seismic data agree, the interior model becomes harder to dismiss. It becomes less like a theory and more like a solution that fits the evidence. Magnetism, the invisible shield that proves motion. And then there's Earth's magnetic field. From space, it wraps the planet like a protective geometry. It has structure. It changes over time. It drifts. It pulses in response to solar activity. That changing quality is important. A permanent magnet would not behave like this, and it could not exist at core temperatures. So the interior must contain a moving conductor, a fluid layer capable of generating a magnetic field through motion. That is the outer core, a circulating ocean of metal, deep beneath the mantle. From orbit, no one can see it, but the field it creates reaches far above the atmosphere, far enough that spacecraft can measure it directly. In a sense, Earth's core announces itself to space, not with light, with magnetism. The most reassuring pattern, different methods agree. At the end of the day, the strongest reason we trust Earth's interior model is not any single measurement. It's convergence. Seismic waves show a liquid layer where S waves vanish and where P waves bend sharply. Reflections and subtle arrivals reveal a solid inner core inside that liquid. Gravity confirms that dense material must exist deep inside the planet. Magnetism confirms that a conducting fluid is moving down there, generating a field. Meteorites and planetary formation physics explain why iron and nickel would sink inward while silicates rise. Laboratory experiments recreate extreme pressures and temperatures, showing how materials behave under core-like conditions. Each of these lines of evidence is imperfect alone. Together, they become a mesh, and the picture holds: crust, mantle, liquid outer core, solid inner core, not as a belief, as a model that survives contact with the real world, a gentle return to the original question. So, how do we know what's inside Earth? Because Earth is not a locked box. It is an instrument, that plays itself, sometimes softly, all the time, sometimes loudly during earthquakes. And the waves it produces are readable if you have enough patience, enough sensors, and enough time. From orbit, the planet looks smooth. From within the data, it looks layered, and there's something quietly calming in that. Even when we can't reach a place directly, the universe still allows us to understand it, not through force, through observation, through listening. Closing image. Now, the camera of imagination drifts back. The United States becomes a pattern of lights and coastlines again. The oceans return to blue. The clouds return to white. Earth becomes what it always was from this distance, a bright, turning world in a dark sky. But the idea stays. Beneath that calm surface is motion, slow convection, circulating metal, layers under pressure, boundaries traced by waves. A planet with a deep interior that has been shaping the surface for billions of years. And it can be known, not perfectly, not completely, but enough to be real in the mind, enough to be mapped, enough to be trusted. And for tonight, that's a good place to rest. A world that looks quiet from far away and makes sense when you listen closely.